I was going to do one example of sketching a rational function um, using some calculus, something you'd see in 3.6 in our homework. Anyways, we're going to sketch f of x equals x cubed over x squared minus 9. And, I need to know about the domain because things can happen in terms of increasing, decreasing, and also concavity when there's, problem areas like asymptotes or something not in the domain. So the denominator is going to be 0 when x is equal to plus or minus 3. So that's our restrictions for our domain. Our intercept is just going to be 0, 0. Sometimes you have more than one, but that's the only intercept we have. So to find the x-intercept, that y equals 0, solve for x. To find the y-intercept, you let x equal 0. So we just have one intercept at 0, 0. Your vertical asymptotes a lot of times are going to be where you have restrictions in your domain. So your vertical asymptotes are going to be plus and minus 3. We do have a slant asymptote because the degree of the denominator is 1 less than the degree of the numerator, or the numerator's degree is 1 greater than the degree of the denominator. Because x squared minus 9 is not linear, we have to use good old long division, and our that's supposed to be a cube here. And our quotient, we don't care about the remainder, our quotient is going to be our slant, because the rest of it's going to go to 0. So our slant asymptote in this case is y equals x. So there's going to be a number of things that we'll graph. We'll graph our asymptotes, we'll graph our intercepts, we'll graph our mins and our maxes. And the mins and the maxes, we can use the first derivative test, which requires us to take the derivative. So if I take the derivative of this, first we'll just rewrite the function. So it's low, which is x squared minus 9, and then d high, which is 3x squared, minus the high function, which is x cubed times the derivative of the low, which is 2x, all over the denominator squared. We'll go ahead and clean that up a little bit. So we got x to the fourth minus 27 x squared all over x squared minus 9 quantity squared. We'll clean it up a little bit further. A fraction is equal to 0 when the numerator is equal to 0. So when x squared times x squared minus 27 is equal to 0. So when the x squared is equal to 0, that's when x is 0. X squared minus 27. So x squared minus 27 equals 0. When x squared is equal to 27, so then we'd have to take the square root. So x would be equal to plus or minus square root of 27, which is 3 root 3, plus or minus 3 root 3. So that's what's going on there. I'm not going to show all that work, though. There it was. And there it goes. Okay. Or x is equal to plus or minus 3 root 3, which is about 5.2. Okay, so that's where I may have some horizontal tangents. Those are some critical numbers. 3 and negative 3 are not critical numbers because they're not part of the original function. So critical numbers where the original function was defined at that number and the first derivative was undefined, or it was 0, so you had a horizontal tangent. Okay, so we'll draw our number line, and we'll put in our critical numbers and then any values of x that are not in the domain, and then we'll go ahead and test in each interval. So we're testing for positive or negative. So really the only thing that matters is that x squared minus 27. The x squared outside is always going to be positive. The x squared minus 9 quantity squared is always going to be positive. It's only that x squared minus 27 that's going to change signs. Okay, when we're larger than negative 3 root 3, like 4, negative 4 squared is 64, and that's certainly larger than 27, so that'd be positive. So we're increasing from negative infinity to negative 3 root 3. Then if we pick something between negative 3 root 3 and negative 3, for instance 5, negative 5 lives there. 25 minus 27 is negative, so we're decreasing from negative 3 root 3 to negative 3. Then pick somebody between negative 3 and 0, like negative 1. Negative 1 squared minus 27 is negative 26, so that's negative, so we're decreasing between negative 3 and 0. And then from 0 to 3, plug in 1, same thing. Between 3 and 3 root 3, we'll try something like 4. Again, we'll get 16 minus 27, which is negative, so that's decreasing. And then finally, pick something like larger than 3 root 3, like, I don't know, 6. 6 squared minus 27, that's positive. So we're increasing from 3 root 3 to infinity. So when I change from increasing to decreasing, like at negative 3 root 3, I have a max. And then that, oops, that's not in the right place. That doesn't go there. Do not have a min right here. We have a min at 3 root 3. Okay. So we have a relative max at negative 3 root 3, and then I went ahead and plugged that into the original function. So I got negative 7.79 in the original function. And then a relative min, 3 root 3 and 7.79, and I got that from the original function by plugging 3 root 3 in. So the original function will tell you position, the first derivative will tell you about increasing, decreasing, and the second derivative will tell you about concavity. So you just got to remember what you're looking for. So when we plot some points, maybe you want to write this down if you're following along, that I'm going to plot those points along with our intercept at 0, 0. I'm going to plot the asymptotes, and then I'll mention what I know about increasing, decreasing, and then we'll go after the concavity also. So the real fun part is taking that second derivative. So first we'll write the first derivative over again, and then we'll just take the derivative of the first derivative. Okay. So it's going to be low, which is the x squared minus 9 quantity squared, times the derivative of the top, and the derivative of the top is 4x cubed minus 54x, times the high, oops, should be 54, should just be 54x. Sorry, we get excited sometimes and add in a little bit of extra things. Okay, just 54x. And then we have high function times the derivative of the low, and we're going to have to use the chain rule, so the 2 is going to come down, and then the base, x squared minus 9, times the derivative of the inside, which would be 2x, all over the denominator squared, so squared squared would be the 4th power, equals squared. So what happened here is I have a common factor, so I can, of the x squares minus 9, so I went ahead and canceled that out. So that's gone. One factor is gone. Okay. And then that 2 and the 2x are going to make a 4x times the x to the 4th minus 27. And then it's just some algebra, a little bit of foiling, a little bit of combining like terms. It's not that exciting. So that's what's going on right here. Some nice things are going to happen, and you can only be left with a cube term and a, I think, what was it, a cube term and an x term. So everybody else is going to take off or combine. Okay, and that's all over this x squared minus 9 to the 3rd power. Okay, so we'll move on to the next slide. So what's left is 18x cubed plus 486x all over x squared minus 9 quantity cubed. There's an 18x as a GCF, so we'll go ahead and factor that out. And then we'll talk about concavity. So we'll look at concavity. We need to look at where we may have the denominator, or where the function was undefined, so that would be minus 3 and 3. We got to check out what's going on there. And then we also got to check where the second derivative is equal to 0. Well, the only time the second derivative is equal to 0 is when that 18x is equal to 0, which means the x is equal to 0. X squared plus 27 is always positive, so in it, it's not going to change anything. So we're going to put in -3, 0, and 3, and we're going to test around them. So when I put in like a big negative, upstairs, that's going to be a positive times the negative, so that's negative, and then downstairs, that will be positive. So the result is negative, so if it's negative, we're concave down from negative infinity to -3. We are concave up from -3 to 0. If we plug something in, our first derivative or our second derivative will be positive. So for instance, you could have plugged -1 into the second derivative, and then a 1, and then, I don't know, 4. And we'd have similar behavior. Because we changed concavity at 0, we have a point of inflection. We do not have points of inflection at -3 and 3 because they're not in the domain. So no point of inflection. So sometimes we change concavity at asymptotes or something that's not in the domain. Okay, so we're going to put all this together. Maybe you want to take a moment to write down the intervals of increasing, decreasing, and also the intervals of concave up, concave down. And then we'll also plug in our min and max and our intercepts. So we're going to go ahead and graph all of that stuff. So I felt like going up by 5s, put in my vertical asymptotes, x equals -3 and x equals 3. Put in my slant asymptote, y equals x. Put in my min, and I know that I am increasing, so I knew I was increasing, and from this is that 3√3, so from 3√3 to infinity I was increasing. I also know it's concave up, and then I was decreasing from -3 to 3√3 from the first derivative. Okay, we got this nice concave up. There's our minimum, and then I'll put in my x-intercept, and I know that from -3 to 0 it was decreasing, and we knew that it was all concave up from -3 to 0. So we got concave up. We got our point of inflection at 0, and we are decreasing from 0 to 3, and then it changes to concave down. So that's all that information we found for the first and second derivatives. Now I'll put in our other point, our maximum. It was about -5.2 and -7.79, and that was that -3√3. So that's right there. We knew that we were increasing